This is the acceleration review video. And so we've already done velocity equals distance over time. Now I want to get into acceleration is the change in velocity divided by the time. So this triangle here, delta, means change in. Okay, so this is how much the velocity has changed. And so you're going to see in this review that we're going to be noticing the velocity change all the time because that's what acceleration is. It's the velocity that's changing. If it's staying the same, cruise control, or when you're stopped, your velocity is not changing, you're not accelerating. So velocity has to be changing. We're going to start just by looking at the right here, and we're going to determine the unit type. So if we see 3.12, we don't know what we're talking about. But once we see this meters per second, then we know this is referring to a speed. And so this is a velocity, so V for velocity. When we see 88 m, the 88 we don't know, but the m means this is a meters. So if we use it in context, I went 88 meters, right? That means a distance. And so this would be the letter D is associated with meters. 38H means hours. Hours is a unit of time, so this would be T. Now we get to something like this, 650 meters per second. That's a speed, but there's another per second, which means the speed is changing every second. And so what this is an acceleration. So that's the letter A. A for acceleration, because it's three things, meters per second per second. So even though there is an m, which means distance, there's also a time, and there's another time. And so your distance is changing over time, which is also changing over time, which means what we're talking about is a speed that is changing, that's acceleration. So every time we see these three units, distance, time, time, we're thinking acceleration. Well, look at this. It's 17 meters per second squared. This is distance, time, twice. Distance, time, time. And so this is also an acceleration. Okay, here we have just a seconds. Okay, it's 212 s seconds. So because there's nothing else, this is simply a time. And this last one, this is kilometers per hour. Okay, we got a distance divided by a time. That's changing distance. That is what we call speed, velocity. All right, so this is a velocity. So hopefully we can identify these things as we go. For each of the first few, we're going to be determining acceleration. Each question is a little bit different. A dog speeds up 300 meters per second in 25 seconds. Well, acceleration is a change in speed. And this is how much the speed changed. That's v over the time, which is t. And so acceleration, I'll write this using my equation tool. Acceleration equals the change in speed, which is 300, divided by the time, which is 25. And what do we get? We get 300 divided by 25 gives us 12. And our units are meters per second squared. Okay, because those are the units for acceleration if it's meters per second per second. Okay, meters per second squared, just like this. A cat speeds up from 0 to 7 meters per second in 1.2 seconds. All right, it started at 0, went to 7. What's the change in velocity? The change in velocity, okay, is 7. So 7 is our change in velocity. And this is our time, 1.2 seconds. And so what are we going to do? Acceleration is change in velocity divided by time. So we got A equals 7 divided by 1.2. And we get an answer of 7 over 1.2, 5.83 meters per second squared. Because it's meters per second per second. There we go. The car can accelerate from 50 to 80 kilometers an hour in 2.5 seconds. We have two different speeds here. What we did here too, here is clear that the change was 7. What's the change here? Remember that we care about the change in velocity if we want acceleration, okay? And that's what we're asking for, acceleration. And so we need the change. How much did it change? Well, it went up by 30. So the change in velocity, if we look at these two numbers, is 30 kilometers. Oops, that's not what I want to try. Change in velocity is 30 kilometers per hour. Okay, so we don't really care. Well, we need the 50 and the 80 to figure that out, but this is the number we want to use. We want to use 30 in our formula. And so Same thing we've done. Acceleration equals, now it's 30 kilometers per hour divided by 2.5 seconds. And that gives us, this is kilometers per hour, and this is 2.5 seconds. And that gives us a final answer of 30 over 2.5 is 12 again. Meter, oh, what are our units here? 12 kilometers per hour per second. Wow, that's kind of a confusing equation there, but that's what it is. It's 12 kilometers per hour every second. That's how much they're speeding up. And after 2.5 seconds of increasing by 12, you're going to get a change of 30. You're going to move from 50 to 80. That's what's happening. All right. The cyclist speeds up from, now I'm adding direction, 2 meters per second north to 14 meters per second north. Okay, we've seen this before where we've got two different speeds. Remember our formula, we want the change in speed, and so, or in velocity. And so we went from 2 to 14. That's a change. So delta V, the change in speed, is 12 meters per second. And we change that direction, we increase towards the north, right? And so I just maintain my direction because direction's nice. And so what our formula looks like, oh, I should note, once again, we've got the time. I never wrote that last time. This is the time. And so what we end up writing is our acceleration equals the change in velocity, which is 12, not 2 or 14. It's 12 meters per second divided by 4 seconds. Okay, and this was meters per second. And so this will help us find our units. And this gives us an answer of 3 meters per second, okay, or meters per second squared. So 3 meters per second squared would be another acceptable answer. 3 meters per second squared. Another very acceptable answer. You don't have to format it the way Cami does, but this is fine. Okay, 3 meters per second per second. So one more of these questions. This one's tricky. We got direction. Oh, I didn't write direction in the last one. Okay, so this would be, the answer would be towards the north, the same as the change in velocity. This velocity was speeding up towards the north. Okay, now that's where this one gets a bit tricky here. A car changes speed from 25 meters per second west to 5 meters per second west. And so this is a change of 20, but it went down 20. So I make this negative. So the change in velocity is negative this time, 20 meters per second west. Okay, that you could write this as, the other thing is it might have just changed positive 20 meters per second towards the east, right? This is the same thing. Now, whichever one you like better is good. And of course, this is our time. And so once again, we are going to use our equation. Our acceleration is change of 20 divided by 1.8 seconds, 20 meters per second, and that gives us 20 over 1.8 is 11.1 meters per second per second. Okay, meters per second, and again per second. Seconds there. But what direction will we have here? East. Okay, because it slowed down towards the west, and so the acceleration was towards the east. Okay, or you could have had negative 11.1 meters per second west. But the big thing is his speed was changing opposite of west. He was slowing down, so his speed is changing towards the east. That's a weird one. The direction there makes this very weird. We still found the change. How much did it change? Changed 20 in 1.8 seconds. So we didn't use either. If you've got two speeds, you find the difference. This is a big deal, this triangle. You have to find how much it changed. And so let's do a couple questions here. A golf ball is hit and accelerates from rest at 3,120 meters per second squared for 0.0125 seconds. How fast is the ball moving after that hit? Now I'm going to draw out our triangle here. A equals delta V, remember the change makes a big difference, over T. There is our triangle. In this case, we're wondering how fast. So we're looking for the change in velocity. We know that it started at 0, and so we are going to find that. So that would be A equals T. So our formula is going to be our change in velocity is our acceleration multiplied by our time. Okay, and so what we're going to find is delta V equals our acceleration. Now, what is what here? We see this meters per second squared, so we know this 3120 is our acceleration because meters per second squared is an acceleration unit. We see this is seconds, so we know that this is time here. And so delta V is our A times our T, so we're going to get A of 3120 times our time of 0.0125. We get 3120 times 0.0125, 39 meters per second. There's our time, our speed, sorry. There's our speed, there's our answer. Okay, so after that much time getting hit with that acceleration, that's what the ball's going to do. A skydiver jumps from a plane, accelerates. Oh, it says accelerates, that gives us a hint, and it's meters per second squared. There's the other hint, this is an acceleration. Okay, until he reaches his terminal velocity of this. Okay, this is a velocity. Assuming a constant acceleration until that time, how long does it take for the skydiver to reach his terminal velocity? All right, he's jumping from a plane, and so he accelerated from rest to that. And so we know his change in velocity was 56, right? It's not just any velocity, it's the change in it. We also know the acceleration was that, and we want to find the time, how long. So we're looking for the time, so we're going to do change in velocity divided by A. So time equals change in velocity divided by the acceleration. That's from this formula. And so, erase this. So we plug in our values. T equals, change in velocity was 56, divided by 9.8 meters per second squared. That equals 56 over 9.8 is 5.7 seconds. Okay, so it takes him 5.7 seconds of falling before he even reaches his full speed. All right, that's pretty cool. All right, last question. Please pause and try this yourself. And then watch the video once you're done. What we have here is 1.1 meters per second. This is our speed. Okay, and this is our first speed. This is where we started. Because now it's going to pick up speed before it jumps on another branch. So it accelerates. Oh, accelerates meters per second squared. This is an acceleration. Everything's pointing towards acceleration. And for this much s seconds time. Okay, so we've got v, a, and t. So can we just we need to not know something. What's the speed the cat reaches before jumping? Remember, this gives us the change in velocity. This gives us its starting velocity, but not how much it changed, right? And what we're actually looking for isn't the change. We're looking for the final velocity. So we got to figure out how much it changes and add it to its initial, because the change doesn't know what its starting speed is, but we do. And so let's figure out what the change in velocity is. And so that would be, we're looking for the change in velocity. And so change in velocity equals a times t. Oh, we've done this before. All right, and so what this looks like is delta v, capital delta v equals our acceleration of 11.8 meters per second squared times 0.8 seconds. It gives us 11.8 times 0.8 is 9.44. That is meters per second. That's how much we have sped up. Okay, this is not our final answer, because now we have to consider our starting speed. And so v2, in this case, our final speed, is going to equal our initial speed of 1.1 plus our change in speed of 9.4. And that gives us 10.5 meters per second. And that's our final speed. So we have to be careful there, not just to accept this as our final answer, because it's not. We have to then add the initial, okay? The initial speed plus our change, right? Delta for change, and then we get our final answer of that. All right, so that's it. If you have more questions, please ask. I encourage you now you've had some extra training, to go back to the reviews that we've got and try out those questions. Look to the key for answers and keep asking questions if you have them. But now go back to the review and try out more questions on your own.